Alright, hi everyone. Welcome to our lecture on debugging in C. Just a couple of notes on the debugging etymology here. If you go check out this link, which is a great little analysis of a software bug, we'll learn about Grace Hopper and a few other pioneers that were instrumental in coming up with the term bug, and specifically about how it didn't originate with computer science. It originated with systems and designs and machines from an earlier age. And there's a great picture here. Let's see if I can drag it over, of a software bug here from the Harvard Mark II electromechanical computers log, where the Grace Hopper, they identified, her team found an actual moth stuck in a relay and taped it into the logbook, and they made the note that it was the first case of a bug actually being found. A bit of a misnomer there. It wasn't the first case of a bug being found, but it might have been the actual first case of a bug physically wrecking a computer. So an interesting little story. For our purposes, bugs are going to be those things that make your program stop working, or they help either show a flaw in the programming design, or maybe simply a syntactical issue. One of the first things that we want to do is we want to be able to reproduce that problem. So is it something that we can easily trigger over and over again, or is it something that's intermittent? And intermittent bugs are much more difficult to solve than ones that are reliably reproduced. So we first want to simplify our input and simplify the environment down until the problem can be replicated at will. That's one of the first steps to do when we're trying to nail down a bug. So we talked about the wolf fence algorithm in an earlier lecture, but basically sometimes this means commenting out whole swaths of your code until you get it down to a portion that's manageable. And there are challenges in doing that. There are unique environments that make it difficult to go back to where we were before. There may be a particular sequence of events leading up to the error that are unknown, or they're difficult to do more than once. For the three types, this is a slide from the previous lecture, but we talked about live examination, post-mortem debugging, and trace statements. And today we are going to look at live examination. So using a debugger with GCC. So GCC by itself doesn't have a debugger, but we can tell the software to compile with all of the flags built into it. So when we use -G, we're saying load in all those symbols that map human-readable words and names to variables, so that when you output errors, when we find errors in the code, we can refer to those errors by name and not just random numbers and addresses. So -G makes that all possible. Then we're going to start the debugger up simply by saying gdb and then the path to the program that we want to launch it in there. Inside the debugger, some of the key commands that we'll be using are run, which will start or restart the program running. The flow of execution will pause at breakpoints, and we can add breakpoints in to stop the program at particular times, or particular lines of code. We can even add different arguments to the given run, like if executing the program requires an integer and then some file path, then you can add those to the run statement when you type it. Breakpoint is how we set breakpoints in the debugger. That's where it stops, and it's break and then a line number. And we'll do a demonstration of how that works coming up here. Step executes a single line of code, and it will enter the function call, which is a critical difference because the keyword next will step over a function. It will simply run the entire function and then go to the next line. So this will execute the single line but will not enter the function call. Continue is used for once the program execution has paused at a breakpoint, we can start up the execution again by using continue. Print will tell us the value of a variable, and quit is how we get out. Alright, so if you look at the lecture lists that we have online, you'll see that there is a sample file, testit.c, that goes along with this lecture. So I recommend that you grab that file, copy it up to our server, and go ahead and follow along with me line by line here, and you'll be able to run this debugging example for yourself. I think it'll be very instructional that way. So let's take a look at the compilation step. Nothing particularly strange. We're going to call our program testit, and it comes from testit.c. And when I run it, it immediately just gives me a seg fault. Well, that's a bummer. Let's see if we can figure out why. This time, we're going to compile it with the G flag, and that will give us the debug symbols we're going to need. Then we'll go ahead and start up GDB with our program. And note, we didn't need any arguments for our program, so we just GDB test it. And it launches it up, and here it goes. And then we can tell it's going to add a whole bunch of crud in here that you can pretty much ignore. And then the last step is going to say that it's reading the symbols in from our program. So that's a good thing. Now run, and actually I misspoke earlier, we don't put the arguments here for test it, you put the arguments here for run. And that will enable us to change, if we have different instances of run that we want to do, we can specify those every time we type run. When we do that, it'll tell us that the program has started, and then it tells us that we segfault right off at line 12. And it seems to have something to do with taking this character and putting it inside this array, or assigning its value into the array. Something about that is causing an immediate segfault. Now from our previous lectures, we have an idea. Segfaults are commonly caused by trying to write into strings, or trying to write into read-only strings. So let's see if that's the case. We're going to set a breakpoint at line 12. What that will do is it will stop the program just before it executes that line. So we'll set it at 12. Then we'll type run again, and it'll tell us, hey, this program's already been starting, has already started. Do you want to start it again from the beginning? Type yes, and it'll keep going. Starts it up, and it'll give us this output here. Breakpoint 1 in the main function at testit.c line 10. That's where it stops. And then number 12 here is the next line that it's going to execute. So line 11 is a new line, there's nothing in it, and then line 12 is this line here. And it tells us this is where the issue is. Or at least that's where our breakpoint is. And we know that's where the issue is because it told us on a previous crash that's where the issue is. So then we can print out the value of temp. Maybe there's something in there that's causing an issue. So when we say print temp, it will tell us here is the current contents of temp. And it looks like it's a string array. This $1 over here is merely a way to keep track of every time we call a print statement. It'll give this number over here will increment. That helps us to tell later as we read the playback of this test. We'll be able to see that each one was a different one. It's not the same value being given every time, but it's a different line number, or it's a different execution number every time. So then I can use the command list 12. And what that will do is it will list the 5 lines before and after line 12. So in this case, it shows us the line that we're just about to execute, and that is simply an assignment of a character into the array. But up here on line 7, we can see that this variable was declared as a string literal, so that the segfault makes perfect sense. You cannot do this. And this is in read-only memory, and it cannot be accessed. It cannot be accessed for assignment down here. So not allowed to modify that string literal. Here is our code again, just for our next line here for remembering. What I'm going to do now is run jump 13. And what that's going to do is it's going to jump over from where we are. It's going to skip line 12 and re-begin at line 13. When I do that, it then jumps it, goes to line 13, and starts running again. So the program starts, outputs the text CS344, which was the output of this for loop down here, and then it says adding 6 to 3, and it got 10, which is clearly not right, and then exits the program. So we might have dodged this particular error, but we still encountered that there is something wrong with this particular program. So we'll set a breakpoint at line 13 because jumping line 13, or jumping to line 13 was nice, but starting up execution and then running was not so handy. So we'll set a breakpoint at 13. And just to demonstrate a new command here, info breakpoints tells us information about the breakpoints. We can see that we have 2 set, and that this one is at line 12, that this one's at line 13, and it'll even tell us that in this particular session of GDB, our breakpoint at line 12 was hit 1 time, so that's handy. Then we'll start run again, and since our program had already finished, we don't get the warning about, hey, do you want to start over again? It just starts, and it hits breakpoint 1 at line 12. It's just about to do this, and it's paused the execution. This time we type jump 13 to jump to line 13. It tells us it starts continuing again, and then it immediately stops again, so that we can pause and see what we need to do next. The next line it's going to do is going to be line 14, and it's this the constraints for the for loop that's coming. So the next thing we'll do is we will start stepping through this for loop. So we'll use the step command to go ahead and execute the line we were just looking at, which was the header for this for loop. And it will then tell us what the next thing is. So we run step, and then we'll go ahead and print out I. Well, I is currently 0. So that makes sense. In our previous listing here, we can see that I starts as 0, so it's no surprise that when we print it out, the value is 0. We'll run step again, and now we've outputted the letter C, which makes sense because that was the printf statement. And it's when we look at what the next step is, we're back at the for loop header, which makes sense. The loop is going to continue back up to this point. Print out I, it's still 0 as of this point because this is the next line that we're going to run. We have not yet run it, so this I++ has not yet executed. Now we run step, which does this I++ and moves to the next line, ready to run it. Now when we print out I, we can see that I has finally updated. We can use the where command to tell us where we are. Just as a touch point, as a way to reference what's going on. Just as a reminder, we can see that we're in main and that we're just about to do line 15. Here, we say, you know what, there's going to be a lot more loops of that for loop. Let's stop trying to run those through every iteration. We're just going to set a breakpoint a little bit in the future to line 17, and so that we can just jump to it directly. So then we'll run continue, and it will tell us the rest of the parts of the for loop. Bink, 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 just so we can speed this up a little bit. All right, so now that we've run, we have hit our breakpoint, and it tells us that this is the line it's about to run. We see that there is this add function as one of the arguments that is being passed into this decimal field, and that somewhere the guess so far is that add 6 is going to take 3 and add 6 to it and somehow come up with a wrong number. So here's our function. Let's go in. Now here I type next to get to the next line, and that was wrong because what it does is it simply executes the entire line and does not go in. So it tells us the next thing is this brace to tell us that we're out of scope, or that we're going to be returning our scope here. But that was completely wrong because we didn't get to go into the function. There was an error, but we can't see it because we've stepped over it. We've nexted over it. So that's a bummer. We're going to have to restart this particular run. And you'll find that your test cases of using GDB and in using all live debugging tools, you'll often have this problem. You'll start running, you'll see that there's a problem, and you'll have to restart your debug in order to try to find what that particular issue is. Where tells us, yep, I'm at line 18, not where I want to be. So run to restart the whole thing, jump at 13, and then our breakpoint is still there, so our breakpoint stops us at the next part. Then we're going to continue, and that will continue down to our next breakpoint, the one at 17. This stopping here at 13 was necessary to dodge that seg fault error that's still in the code. Now we can run step to step into the function. And GDB will tell us, all right, you're now in the function. So now we're in add 6, and it'll tell us what the value of the variable was that we came in with. And right here it tells us, line 22, that the integer called 6 was set equal to 7, and it should have been 6. So we can set a watch point on 6. This is a handy tool. This lets us know, or it will pause execution whenever the variable 6 changes, which is a powerful way to say, I don't know when this is going to happen somewhere in this code, but I know it happens somewhere, so just start running and then have the program stop when that watch point gets hit. So watch is going to cause GDB to pause execution if the variable 6 changes. And we could have written this out as a whole expression here. We could say watch 6 if 6 is greater than 6. So that also would have found the same problem. This could be, as complicated as you want to try to find a particular circumstance for where some variable goes to a value that you did not expect it to go to. So we go next, and we will step to the next line here. And the watch point triggers, and it tells us that the old value of this particular variable has changed from 52 to 7. And that is happening simply in this initial assignment declaration line. So the garbage value that started with was 52, and it has now been updated to 7. And it tells us that our next line is to return 6 plus whatever the thing that came into the function was, which was 3. So 3 plus the 7 is going to give us 10. We can hit continue, and we see that it returns. What it does here is it pauses because we've now left the scope where this watch point existed. So GDB deletes the watch point, tells us about it, and returns back to main at line 17 where this add 6 is. Type continue again, and it will continue, finish, and exit, telling us it's still displaying the same error. And then we can quit with quit. Well, now we've identified where both of those errors are within the code. We can go in and change those. Okay, so Visual Studio and pretty much any other integrated development environment is going to be way better than GCC and GDB combined. So the really good IDEs will have not only the code generation, and which includes automatic completion of names and whatever the namespaces that are in. It can match up curly braces, from start to finish. It can match up ifs and elses and thens, so you can figure out what's wrong with those. It does the compilation and all the optimizing built in, the organization in terms of setting up all the different files that you might be using in your program, and the live debugging and code step through built into the editor. It's very powerful, and even automatic documentation as it goes. Visual Studio is amazing stuff. But we don't have access to that in this command line environment in Unix. And when we're trying to develop directly on this server, we can't really take the code, move it over to Visual Studio, compile it, and run it on a Windows machine and bring it back, because that Windows machine is a totally different set of software and libraries installed than our Unix machine. So we really do have to get comfortable finding these kind of problems on Unix. Another tool that we can use that can be helpful is called valgrind. And valgrind can help us find memory leaks in C. And we do want to compile with -G when we work with our software here, because it will add better diagnostic information to valgrind. So if you're going to use valgrind, also use -G. Here's a program that we have, and it's called leaky.c. It has a bunch of headers. Here's our main function, and in main we're going to declare a pointer to a character called dynamic buffer, and then we're going to malloc it, and then note that the program is done. That's where it happens. So we've got a malloc but with no free. That is a memory leak. So here we compile it with -G so that we can have like line numbers and functions and variable names inside our output. Here's then the example. Here is what I've researched a lot of different ways to run valgrind. This appears to be the way that generates enough information but not too much information. So leak check being on and show reachable being on, and then you specify the name of the program. And it tells us things like this. The heap, it'll tell us about the heap, that there were 10 bytes that were allocated in one block. So let's go back and look at the code for a sec. So we told it to allocate 10 bytes, and we did it with just as one block, not as multiple malloc calls, just one malloc call. So 10 bytes in one block, and then our total usage was 1 allocation, 0 times freed, and 10 bytes allocated. And it gives us this warning. 10 bytes in one block are still reachable in loss record 1 of 1. So malloc and then main, where it was used inside, that we have some bytes that are still reachable, that we can still hit, because we never deleted that particular pointer. So the still reachable is referring to the dynamic buffer whose dynamically allocated memory pointer was not overwritten, but we simply didn't free it before the program terminated. So because the operating system is going to let go all of the memory when your process terminates, you can usually ignore this kind of warning, this kind of error. But again, if we were in a long-term program, having things like this build up over time can kill the system. So it's definitely safest to deallocate those. And you can see that in the summary here, still reachable 10 bytes claims that we could go find those and save and solve them. And one good reason to do that isn't just to improve the software you're running here, but if this ever gets copied and reused in some other program, you want to have the deallocation built into it, so that when it's revised and used and incorporated into something else, you don't propagate this memory leak into some larger program. Alright, so here we have leaky 2. This is a separate version here, and this is going to be a note about using printf and a lot of the standard I/O library with valgrind. So this program is the same, except we have a printf statement down here. And what happens here is that printf, being part of the standard IO library, being non-reentrant, it uses all kinds of internal variables that confuse valgrind into thinking that things are way worse than they actually are. So when we run it, here is the same setup with leaky 2. And what happens is that we still have the 10 bytes in one block as part of our summary here, but valgrind now reports that the 10 bytes in one block are definitely lost. They are irretrievably lost, and that we've completely lost that pointer, which is not the case. If we go back and look at this code, that buffer never was reassigned. So we haven't actually lost this particular address. And in the end here at the summary, you can see that the bytes have been moved from still reachable up into the definitely lost section. So despite this warning, you can still fix your code, but there is still a memory leak if you don't. So printf and the entire standard IO library, be aware they might mess up what valgrind is trying to detect. So this is our leaky 3 version. So in this particular program, we have an integer that's declared, and then we printf right out from it. Well, 6 was never initialized in this particular example. So valgrind can help us discover that we're using things that are not initialized. So in this particular run-through, we can see that with the way valgrind is running, that we have the use of uninitialized value of size 8, and that makes sense because that size 8 comes from our integer. And here was main, printf, and then look at all these other functions that printf was using. So v, fprintf, itoa, so this is converting integers into arrays, all kinds of different stuff used by that printf call. So no wonder valgrind gets confused by it. And so it's really handy to know that we had this problem here. Well, I hope that was instructive. I recommend these tools. They are terrific tools for helping find bugs in your own code. We'll see you at the next lecture. Thanks!